Welcome to the fourth day of Summer General Physics. In this fourth video, we'll be taking a look at relative motion. So as we start to think about relative motion, here's an example to keep in mind. Let's suppose that we have an apple on a sheet of paper, and we have two different coordinate systems, or frames of reference. A frame of reference just means a particular choice of coordinate system. So let's suppose we have one frame of reference, one coordinate system, that's stuck to the sheet of paper. Maybe we've drawn a set of axes on the sheet of paper, and we're using that as our coordinate system to describe the position of the apple. Now let's suppose that the piece of paper is resting on a table, and we have a coordinate system that is affixed to the surface of the table. Now let's take the piece of paper and pull the apple forward by 10 centimeters. According to the frame of reference of the table, according to this coordinate system we have taped to the table, the apple has moved a distance of 10 centimeters. It's undergone a 10 centimeter displacement. However, according to the frame of reference or the coordinate system that's affixed to the paper, since it traveled along with the apple has not moved. Both of these statements, the statement made by the table coordinate system and the one made by the paper coordinate system, are correct because the two have moved relative to each other. And by knowing how the two have moved relative to each other, you can, based on what one coordinate system says, predict what the other one would say. So in this case, the displacement in the table coordinate system is 10 centimeters, and the one in the paper coordinate system is 0 centimeters. So when we add displacements, in the case of the apple, it was pretty simple because the motion was just in one direction. However, displacements are vectors, so you could have motion in more than one direction, and it's important to keep track of the vectors that you're adding in order to go from one coordinate system to the other. So when you do this, there's a pattern that you can follow. So let's say that we have a boat that is going across a river. So if the river were not flowing, this would be the displacement of the boat with respect to the water. But since the river is flowing, the water moves, and this second vector shows us the displacement of the water with respect to the earth. So then if we had a bird's eye view of this boat's motion, we would see the boat move along this third purple line, which is the displacement of the boat with respect to the earth. So in the Earth's coordinate system, the boat moves along this vector. The boat is trying to move along this vector, but it gets pushed by the water. And so we have to add these two vectors in order to come up with the third, the displacement of the boat with respect to the earth, with respect to either an airplane or helicopter hovering overhead, or with respect to a person standing on the shore. So when we're adding these two vectors, one thing that can help us keep straight which vectors we're adding is that they in general follow a certain pattern. So that pattern is that the first subscript matches the first, the last matches the last, and then the inner two subscripts tend to match. And so the way that you should think of these subscripts is the first specifies the object, the second specifies the observer, or the coordinate system that's taking the measurement. So here we're looking for the displacement of the boat with respect to the earth. To get that, we would have to add together the displacement of the boat with respect to the water. That's how the boat would be moving through the water if there were no current, plus the displacement of the water with respect to the earth, which is the current. Down here we can see another important general principle, and that is if we switch the subscripts, if we switch the ordering of the subscripts, we pick up a minus sign. Now why would that be? Well, when we're switching the subscripts, what we're doing is we're switching the observer. We're switching the point of view. We're switching the coordinate system. And if you are doing that, then you will get the opposite kind of motion. To see that, think about riding in a car. Think about riding in the back seat of a car and looking out the window. If you define the forward direction of the car as being the positive direction, then someone outside the car watching you go by would see you being displaced in the positive direction. On the other hand, from your point of view, you see people outside the car moving in the backward direction. So as you move forward, they appear to be moving backward. If you measured their position relative to you, you would see a displacement, but in the minus direction, in the direction opposite the direction that the car is going. So that's the reason for flipping the sign. If you're switching the point of view, then the other object will be moving relative to you in the opposite direction. So for example, if we have an Earth observer here on the shore, and then we have an observer in one of these floating donuts being swept along with the current, then the person being swept along by the current is moving in the positive y direction, as shown in this picture. And so the Earth observer would report positive motion or positive displacement, but the person in the donut would see the dog moving relative to them in the opposite direction or in the minus y direction. And so that's why we say the displacement of the water with respect to the Earth would be opposite the displacement of the Earth with respect to the water. So here is a question for you as you think about relative displacements. Let's suppose that you're walking down a conveyor belt in the direction that it's moving. Say you're at the airport and you're walking along one of those moving walkways. So there's a dot painted on the belt that travels 10 meters. During the same time, you walk 5 meters along the belt. What is your displacement with respect to the ground? So pause the video here and give some thought to this question, and then start it up again once you have your answer. Okay, so now that you have your answer, let's take a look at the options here. So you are walking down a conveyor belt in the direction that it's moving, and a dot painted on the belt travels 10 meters. So during the same time you're walking 5 meters along the belt. So if you think about your displacement, the displacement of the person who's walking along the belt, the displacement of the person with respect to the belt is 5 meters. You're walking 5 meters along the belt. The displacement of the belt with respect to the Earth is 10 meters. So to get the displacement of the person with respect to the Earth, you would have to add together the displacement with respect to the belt plus how much the belt itself is moving. So 5 meters plus 10 meters, or 15 meters. So the displacement with respect to the Earth for the person on the moving walkway would be a total of 15 meters, or option C. So we've been talking so far about relative displacements. The same sorts of things hold true for velocities. So the description of the velocity also depends on the frame of reference or the coordinate system being used. So for example, let's suppose that a person walks at 3 miles per hour down the aisle of a train and that the train is traveling at 45 miles per hour. So we would say that the velocity of the person with respect to the train is 3 miles per hour. That's how fast they're moving relative to the train car that they're in. The velocity of the train with respect to the Earth, how fast the train is moving, is 45 miles per hour. So if you're a person standing on the surface of the Earth watching the train along with its passenger go by, then if you want to know the velocity of that person with respect to you, you would add together the velocity of the person with respect to the train plus the velocity of the train with respect to the Earth. In this case, these two vectors are pointed in the same direction, so we can just add their magnitudes together, and you would see that the person in the train moving along at 48 miles per hour at a combination of their speed with the speed of the train. So that concludes video 4. In the next video, we will continue considering relative motion. Specifically, we'll be looking at motion in more than one dimension.